Hello everyone, welcome to the lecture series of environmental changes. Today our topic is water scarcity. Before talking about the water scarcity, I want to provide a brief introduction of our available water resource. You already knew about these resources, it is just for refreshing the memory. This is a graphical distribution of the location of water on Earth. 97% of water on the Earth is salt water. Only 3% is freshwater, and two-thirds of this is frozen in glacier and polar ice cap. The remaining unfrozen fresh water is found mainly as groundwater, with only a small fraction present above ground or in the air. So, what is water scarcity? Water scarcity is the lack of sufficient available water resource to meet the demands of water uses within a region. It already affects every continent and around 2.8 billion people around the world, at least 1 month out of water every year. More than 1.2 billion people lack access to clean drinking water, and water abundant areas can be water scarce as well. This map represents the global water scarcity and with some different colors. So different color represents different type of water scarcity, mainly economic water scarcity and physical water scarcity. As you can see, South and North America, mostly they do not have any water scarcity. And in Africa and some regions in Asia, South Asia, they have economic water scarcity. And orange color, it represents physical water scarcity. In our later slides, we will learn more about what are the different water scarcities. Physical water scarcity occurs when and where there is not enough water to meet both human demands and those of ecosystem to function effectively. Arid region frequently suffers from physical water scarcity. It also occurs where water seems abundant but resources are overcommitted. The map in this slide is a map showing average annual precipitation in California. And the California, it has a large geographical variation across the state. So California is a large state with a correspondingly varied climate. As you can see from the figure, some parts of the states are very wet, with close to 100 inches of average precipitation falling annually on its north coast. Southern California, however, is quite dry, with Los Angeles receiving less than 15 inches of rain per year, and the Mojave Desert area to the east receiving less than 5 inches annually. This precipitation is also unevenly distributed across time, with the vast majority occurring over the winter wet season. Economic water scarcity is due to lack of water infrastructure in general or to the poor management of water resources where infrastructure is in place. Economic water scarcity is by far the most disturbing form of water scarcity because it is almost entirely a lack of compassion and good governance that allows the condition to persist. It exists when a population does not have the necessary monetary means to utilize an adequate source of water. It is about an unequal distribution of resources for many reasons, including political and ethnic conflict. Much of sub-Saharan Africa and some parts of South Asia suffers under the effect of this type of water scarcity. So how can we measure the water scarcity? So there is a water scarcity index which measures the pressure on water resources and it can readily apply to multiple watersheds. The index calculates the ratio of annual water withdrawals to annual runoff. Watersheds where withdrawal are less than 20% of supply, that is a ratio of less than 0.2, have low or no water stress. Watersheds with a ratio between 0.2 to 0.4 have medium stress. And watersheds where withdrawals are greater than 40% of supply, that is a ratio of greater than 0.4, have high stress. The threshold of withdrawals being greater than 40% of supply has been arbitrarily chosen amongst the scientific water resources modeling community as an indicator of high water stress. Since the larger the amount of water that is withdrawn from the environment and used and discharged back into the rivers, the more degraded or depleted the resource becomes, and the higher the water stress. In this sense, 100% of resource does not need to be withdrawn for a watershed to be classed as water stressed. The Water Resources Vulnerability Index tends to highlight pressure in watersheds with large amounts of irrigation because the index is largely based upon withdrawals. Projections of future withdrawals are contingent upon the future population change and assumptions about future changes in domestic, industrial, and agricultural water use intensity. However, this metric does not account for water quality. In order to determine the water stress index for every watershed in the contiguous United States, national scale datasets depicting water use and water availability were needed in consistent format and scales. The USGS identifies national hydrologic region using a nested series of hydrologic unit codes, HUC. So our WSI is a metric to denote areas of concern for freshwater sustainability calculated as the ratio of demand over supply. In this case, WSI values was calculated for each individual HUC 8. So it is surface water withdrawals over stream flow supply. Stream flow supply has been calculated for HUC 8 based on WaterWatch USGS data, and surface water withdrawal data has been gathered from USGS water use data as they compiled all the water uses for every county for the last 30 years. Water stress index, also known as water scarcity index. From this map, you can see most of the water stressed areas are in the western part of US, which is a combination of low runoff, precipitation, and higher demand of water. So groundwater recharge stress index is calculated the same way as calculated for surface water stress index. The groundwater withdrawal rates, these values are pretty straightforward. These values are provided by USGS. So this is a cumulative water withdrawal, groundwater withdrawal values from USGS and divided by the groundwater recharge rates. The groundwater recharge rates is also found in the USGS website. The another way of groundwater stress index is the groundwater withdrawal minus the recharge rate, and then we divide it by groundwater supply. Okay, this map of USA is the result of groundwater stress index equation. So the values more than one, which are red, means water withdrawal exceed recharge. Much of the western US, especially California and the high plains, have high withdrawal rates and low recharge rates, making this region more unsustainable. And the places which is in Florida and some places in the Mississippi River basin close to Mississippi, they are also fall under this region, which means the recharge rate is lower than the withdrawal of the groundwater. Groundwater stress index values which are greater than 0.4 means water withdrawals in excess of recharge are high relative to current aquifer storage. This figure shows that much of the US has high storage relative to current usage rates. So even if withdrawal exceeds recharge that you have seen in the previous slide, relative to total storage, the number is small. The exception is Southern California and Arizona, where stored groundwater cannot continue to meet demands. So, what is the reason for this groundwater scarcity? As USGS has done a great job on data compilation of different water use, irrigated area of each county of each state for last 30 years, we took the advantage of this data and explored them. As for example, the map on the left side which shows cumulative groundwater withdrawals from 1985 to 2010. Deep blue color means higher water withdrawals and light blue means lower withdrawals. County level groundwater use data reported by USGS was used to analyze the groundwater withdrawal pattern. The majority of the total groundwater withdrawals were in the western states and along the lower Mississippi River basin. The figure on the right shows the percentage of total groundwater withdrawals for irrigation, where you can see from 1985 to 2010, most of the groundwater withdrawals were for irrigation. Agriculture used the highest fraction of groundwater in 2000. The total amount of groundwater used for irrigation in the previous 30 years is 47 km cube, which triggers groundwater depletion, especially in the western side of US. Groundwater withdrawals rate for irrigation has been increased more than double from 1985 to 2010 due to its stability and accessibility.